Hello, everyone. Thanks for coming back to the second half of Theory Day 1. In case you didn't get enough of neural collapse, Tomer is going to talk a little bit about how it's used in transfer learning. So you saw what it was, and now you'll see why it's useful. So thanks, Tomer.
Thank you for the warm introduction. I'm happy to be here, and I hope you had a great lunch. My name is Tomer. I will talk about the role of neural collapse in transfer learning. I felt like there are many questions around transfer learning regarding neural collapse from the previous talk. So I think that is a good opportunity to continue here. This work couldn't have been done without the amazing collaboration I had with my colleagues from Google DeepMind. So before I start talking about transfer learning, I want to give a little bit of motivation for the problem that we care about, because transfer learning can take many different names, right? For those of you that are familiar with transfer learning, there are many different techniques and approaches to do transfer learning, and we will discuss some of them. So basically, in most of these cases, there is some target problem that we want to solve, right? There is a classification problem, let's say, with multiple classes. And the problem typically is that we have very few samples per class. Okay, so let's say in this example, we have 3 types of cats, and we have 2 samples from each one of the classes. Okay, so we see 2 samples of this type of cat and 2 samples of that one, and so on. And the problem is that directly training on this data set, taking a large neural network or even a small neural network and training the neural network on this specific data set with traditional approaches is not going to be very successful. We're not going to generalize well, and the model that we train is not going to perform very well on nuance in samples. So we kind of want to be able to solve these tasks because, in many cases in our life, we see a problem that we don't have much data around the problem, and we still want to solve that. And I think many of us are familiar with the fact that, okay, we can put the target data aside, and we can try to train our model based on a different source of data. Okay, so we have the target data, and we also have source data, and the source data has many samples, many classes, and basically we can think of it as kind of like a data set that we collected from the internet with a lot of samples. And what we want to do is kind of to come up with a representation of data, some feature map that represents samples that would generalize well to new tasks. We want to pre-train a model that will be able to be effective for the tasks that we actually care about. Okay? By the way, if you have any questions, feel free to raise your hand. I'm very happy to take any questions at any point. So that is basically the goal. Okay? And what we see in practice, I didn't go over specific ways to tackle this problem, to implement this idea, but pre-training is quite fundamental. So one of the main advantages of deep learning is this ability to take some external data set, to train a model on this data set, and then apply to the new task. And it's also kind of like a paradigm shift that we're seeing. So we have these big models like GPT or CLIP or whatever. It changes all the time. And now people are thinking, well, maybe I shouldn't train from scratch. Maybe I should just take a pre-trained model, take a large neural network, and I fine-tune it to the specific task that I care about, where I have much less data. So that is kind of like a new thing that people, or an old idea that people need to consider again, and to think about how to solve these things and what kind of representations and pre-trained models work for these kind of problems. So the questions that I want to tackle today are kind of what is the correct way to pre-train models in specific case of classification, what properties of pre-trained models are useful for transfer learning, what kind of representations we want to obtain to be able to transfer, when should it work, what are the conditions, what assumptions do we need to make to ensure that if I train on one task, it would generalize to new tasks, and to what extent can we reduce the sample complexity of the target task. Okay, so empirically we see that we're able to transfer, and it reduces the number of samples we need to encounter from the target task. But is it like a constant number of samples? Is it like a medium size of data, or we need like a large data set, and we just like improved by a constant the number of samples that we need? So that is another question that we want to discuss. Okay? So let's start with like different ideas. So one approach to solve this task is to say the following. Maybe we can do something that is called FewShot Learning. So in FewShot Learning, basically we try to pre-train the model such that given tasks with few samples, the model will be able to successfully solve these tasks. What does that mean? We basically take the source data with many classes, we split it into many subtasks. So if we had, let's say, 1,000 classes, we generate many three-way classification problems. And for each task, we generate like a data set with few samples. And we train the model such that if we adapt it to a given task with few samples, it would perform well on nuance in samples. Okay, so we train the model such that given a small data set that is used to update the model, then it will perform well on nuance in samples. Okay, so we choose F that minimizes the average error on like the classification of new samples after adapting it with the small data set that we selected. Yeah, I saw a question there. Oh, okay. Are there any other questions? Okay. So this idea goes all the way back to 2016 with matching networks. It's a great idea, and now it's kind of like rebranded as in-context learning. So there is like explicit in context and also like implicit, which is something that we see with language models. But yeah, so this is like a very sound approach, right? And the other way to try to do transfer learning is called transfer learning, which is basically a totally different idea. We take the set of classes, the source data set, and we train a model, a classifier on the whole data set. Okay, so we have, let's say, 1,000 classes, and we train a classifier with 1,000 classes on this data set. Then we basically freeze the bottom layers of the neural network, and we take the small data set for the target task, and we train the top layers again based on the available data from the task that we actually care about. Okay, so we have this process that is very simple, but does not really train the model to successfully solve few-shot learning problems. Right? We don't design the frozen part to be able to tackle new tasks with few samples. So what's surprising is that empirically we see that this second approach is actually kind of competitive on few-shot learning problems with few-shot learning approaches. Okay, so if I use transfer learning, I pre-train a model on all of my classes, and then I take the pre-trained model and I train like a linear classifier on top of it on the available data from a new task with very few samples, then it's generalizing well. It performs well on nuance in samples, even though we did not condition the pre-trained model, the frozen part, to be able to solve these kind of tasks. So I think this is very surprising. Yeah, are there any questions so far? Yeah, yeah. It's one of the things that we will definitely depend on. So you need like to see many source classes. When you do the pre-training, you train with many classes, and we'll try to analyze how this thing, like how seeing many source classes is going to help in learning new tasks. Yeah. So intuition for FewShot Learning? Oh, yeah, I don't want to go into much detail into like, yeah. But basically, so the idea is kind of like you have a neural network, a Siamese network. So it has like two parts, two sides, one for representing like context. So it takes like a batch of samples, which is like conditioning on that. We have like a representation of the task. And we also have another leg to take the sample as input, like the input to the network that we want to classify, and kind of like conditioned on the context, conditioned on the batch of samples, you have like a shared representation of like the task and the specific sample, and we try to classify based on the context, the specific sample. So kind of like the network takes a batch of samples, which is like training, and given that batch of samples, we are able to classify a new sample from the task that is associated with this batch. So surprisingly, yeah, it is better in FewShot than FewShot Learning, which is quite strange, right? Like, because we don't really condition the model to be good for new FewShot tasks. Yeah, you have like the same data set, you decide the same source data set, you decide how to organize it. One way is to split it into many tasks, and another way is like to treat it as one classification problem. And the question is like, how should I organize it? How should I train the model given the organization? And all of that, there are many different, there are plenty of ways to think about how to do it. And it seems that when I compare these two, empirically transfer learning is better. Yeah, so you just sample three-way classification problems from the source data set. So it's kind of like you sample many of them and you train the model like, like online, you see a task, you update the model such that it would generalize given a few samples, blah, blah, blah. And like you train it for a long time until it kind of like converges and you evaluate along the process. Yeah, so I think that now it kind of like moves to the direction of extending the standard setting. So I will try to analyze a very like simple setting in which there is some similarity between the classes. So now we are talking about extending it to what happens if like the tasks are very different and the similarity is low, or maybe not low, but like, that there is some discrepancy between the two tasks. I don't know, maybe like in one case, one is better than the other, but yeah, possibly, yeah. I don't know. The intention here is kind of like to analyze transfer learning, but yeah, it could be very interesting to think about extending the settings and how they could like merge together, yeah. Yeah, so you don't train the model on two samples. You kind of like have one model that if I adapt it to a given task with few samples, it will be good for that task. And then I need to come up with a way to choose this, base model such that it will be good on average for many tasks. So I choose the parameters on the whole like data set of many tasks such that if I adapt it to new tasks, it will, with few samples, it will perform well on these tasks. So like the base model is trained on many tasks, but like the adaptation to a given task is based on few samples every time. Yeah, the adaptation could be affected. Yeah, like seeing more samples obviously is going to change like what you learn. But the goal in FewShot Learning is kind of like to pre-train a model such that if I adapt it to tasks with few samples, it's going to perform well. I want to continue here because like FewShot Learning is less of the main topic of this talk, but these are very interesting questions. I'm happy to talk about these nuances after the talk. So the goal is to explain transfer learning. And the main result is to kind of like to explain the success of transfer learning against FewShot Learning via the notion of neural collapse. Okay, so that is the main thing here. And if I want you to take one thing out of this talk, is this like plan of analysis, like this idea. So the idea is we start with the assumption that we have neural collapse, only NC1. Okay, so we have this clustering property. Essentially, when I train a model on a given training data set, then the embeddings of the samples tend to cluster with respect to their labels. Okay, samples of cats are going to one location in space, and samples of dogs are going to a different location, and so on for each one of the source classes. Okay, and then the second step would be to say, if I see many training samples, okay, so if I trained on a large data set with many samples per class, then this property, this clustering should generalize to new samples. If I look at the test samples from the same task, they also have some clustering pattern, maybe to a lower degree, but if I trained on many training samples, then I expect the test samples to also cluster. That's great. Then I want to say something like this. Okay, we have clustering on the test samples. What about the task that I actually care about? So the claim would be, if I saw many source classes, if I was able to cluster the source classes, and I saw many source classes, then this clustering property should also generalize to nuancing classes. Okay, so if I trained on a gigantic amount of source classes, then if I see new classes, 3 new classes, I expect them to be clustered as well. Okay? And then the idea is that if I achieve this clustering, if it's true, then I don't need to see many samples to train a classifier on top of this embedding space. Okay? I know that these two classes are clustered in their embedding space. Okay? Then if I just pick one sample from each one of these classes, then it's sufficient to be able to come up with like a linear classifier between the two that generalizes well, that will be able to perform well on nuancing samples. Whereas I will need only O of 1, a constant number of samples to be able to like learn a classifier that performs well on nuancing samples. Yeah. So it's contingent on the assumption of neural collapse, and we don't always have neural collapse, as actually demonstrated. It definitely depends on certain conditions, like using some normalizations and weight decay and things like that. So it kind of limits, but also I think it's good because it gives you some form of guideline to when you expect to have representations that would be transferable to new tasks. So I will not give concrete algorithmic like guidelines here for how to get better transfer learning, but it kind of gives you a framework of what is valued when it comes to transfer learning in the setting of like classification to classification. In terms of likelihood, we see that like neural collapse is kind of universal. So we see that it happens with like, as long as the network is deep and over-parameterized and had of the conditions I sorted, It happens for residual networks and non-residual and transformers and whatnot. So it's kind of broad and on many data sets. Okay, so just to have some notations. So the problem is as follows. So we have the target task, K classes. Each one is a distribution of samples, PC. SC is like a batch of samples from this class. Okay, and we have few samples. So let's think of them as like 5 samples. And we have the source task. Everything is with tilde. And we have many samples per class. And this is the algorithm. So we train a model to classify the source data. And then we fix F. And we train a classifier on top of the pre-trained model, F, to classify the data from the target task. Okay? And like neural collapse, so for those of you that were not present in the previous talk, basically the idea is that we train a large neural network for classification on some data set, okay? And then we look at the embeddings of the training samples. They tend to cluster with respect to their class means, okay? So samples from one class are located in one area, and so on. So it looks like that. We have multiple classes and they aggregate in specific locations in space, and they're also kind of like the centers are maximally distant. So it's like the Mercedes-Benz sign. And for our purpose, we will use the following notation for measuring the degree of collapse, which is slightly different than the one actually proposed, but essentially the same thing. So we look at the ratio between the variance of the embeddings of training samples for each one of the classes with respect to the distance squared between the class means. Okay, so we have, like, we measure the variance of the embeddings of each one of the classes, and we look at the square distance between the class means. And just for sanity check, this quantity is scale invariant, right? Like, if I multiply f by 5, then both numerator and denominator would be multiplied by 25, which means that it will not be affected, okay? And our notion of neural collapse would be that when we train the model on the source data set, then the normalized variance would go to 0 during training. So during training, the samples tend to cluster in the embedding space, and it's very nice. And because we look at a slightly different, one sec, no need to apologize. Because we look at a slightly different notion of neural collapse, we looked at this quantity for neural networks of different depth for 3 layers, 5 layers, and so on. And in each one of the lines, we plot the normalized variance on the training data for each one of the layers. And we can see that for very deep networks, for sufficiently deep networks, the top layers tend to collapse. Okay, so it kind of conforms with what actually was talking about, that we see intermediate collapse. So we see kind of like that the top layers have low values for this normalized variance, which means that we have this clustering. So basically, let's say we have some class Q1, okay? So this is like cats, images, and we have F. This is some model that I want to measure its degree of collapse. So it's like a pre-trained model, okay? So we look at the variance of the embeddings given by F of samples from Q1, okay? So we look at the feature embeddings of cats in space. So that's like, we measure the variance of that. So how varied are they, okay? But let's say the variance is very low, okay? And then we look at the variance of dogs now, okay? But potentially, they could have very low variances, but also intersect, right? Like, you have two very small, like small varied classes that kind of intersect. We want to avoid these cases. So we want to say, to what extent are they small compared to their distance? Okay, so that is basically the ratio here. You want to measure, you want this quantity to be small.
So you want it to be small?
Yeah. The smaller it is, the more collapsed the classes are. Because if the variance is small compared to the distance, it means that they are quite clustered. Yeah, it's actually beyond separability. It's a specific type of separability. Yeah, because you could have separability with like high variance, for example. You could have like two large variance circles, for example, linearly separable, but yeah. Okay. So this is for convnets and this is for convresnets. So just for sanity check, y-axis is the quantity and x-axis is the training epoch. So how much did we train? So basically, like each one of these lines is a different layer, okay? And we measure the degree of collapse for each one of them. The lower, the stronger the collapse, and the layers are sorted. So this is the first layer, second layer, and so on. And we see that, you know, like for very deep layers, the degree of collapse is very low. So it's like they are very collapsed. Okay. So now the question that Boris mentioned, what is the relationship between the two tasks? So as mentioned, if the two tasks are very different, then we shouldn't expect to be able to transfer, right? If I train on one task and then I have a completely different task and I learned representations of data of one type of data and then I apply it to a different type of data, then I shouldn't expect any success. Maybe there will be some notion of success, but to a very limited degree. So yeah, so for simplicity, and one could think of extensions of that, we think of the classes as random classes. So basically, let's say we have some generator of classes or like a source of many classes, and we generate the classes from the same generator in an independent fashion. Or like statistically, the classes are independently and identically distributed, okay? So we have some distribution over classes, and the sample and the source classes and the target classes are sampled from the same distribution, okay? Intuitively, we could think of them as kind of like random classes from like ImageNet-like data set with a lot of classes. We have 20,000 classes. We generated 1,000 of them for training, and now we receive 5 more for like evaluating the performance on a new task. Okay, that's the idea. So we have lots of classes. For training, we took airplane, bird, cat, deer, and for testing, we took frog, horse, sheep, truck, randomly. Okay, so that doesn't cover all possible cases. Transfer learning is definitely a more complicated problem than just that, but I think it's a reasonable start. Like we can analyze transfer learning even in this setting and get interesting ideas. Okay? So what is the objective? This is the part that gets a little bit mathy. What is the objective? What do we want to measure? How do we measure success in transfer learning? So the idea is, okay, we have this source task, but now I have some pre-trained model. I want to measure its performance on a new task. But what is this new task? It's basically a random selection of a task. So we think of the new task as a random task from this distribution over tasks. Okay, so this is like a downstream task, and we want to be able to solve tasks on average. So we have like a new task that we encounter, and we want to be able to solve it with few samples. So we have a downstream task with random classes from the distribution over classes, and we take few samples from each one of the classes. So we take 5 samples from the first class and 5 from the second, and so on. We create a linear classifier on top of the model. Okay, so we have the pre-trained model. We train some classifier on top of it based on the few samples. So this is the adaptation to the specific task. We want to measure its performance. So the idea is as follows. This would be like the FewShot error, the expected FewShot error performance of the pre-trained model F. We generate a random target task by selecting the target classes. We select few samples from each one of the classes. Okay, so we take expectation over the selection of the data, and we measure the performance on the given task. Okay, so we have this classifier that is given by F, adapted to the few samples, and we measure the performance in expectation over new samples from this new task, the downstream task. Okay? I want to have some questions. Yeah, so that's a good intuition. Basically, you need to implicitly, from like the later results, to assume that there is some model that is able to handle all of these tasks at the same time. So like they are not just an arbitrary collection. The complexity of solving them all together should be reasonable. Yeah. And that is kind of like trade-off between like the complexity of the model that you choose and like the sizes of the data and so on. Yeah. Oh, the randomness is given by the sets. So I selected like a random set of samples for each one of the classes. Okay, and the classifier is a function of the data. Because the data is random, makes the classifier also random. Yeah. Fair, yeah, you can definitely do that. It's up to you how to define this F, how you choose F. You could take like the top layer, you could take the layer before, you could take half of a layer. Everything is fine here, yeah. No, in practice it's much more messy. Like, sometimes it's like the top layer, sometimes it's like some intermediate layer, and there are many like heuristics around it, and people do fine-tuning, obviously, like update the whole network, and there are many different ways of doing this fine-tuning process and all that, so yeah. But for simplicity, we can think of like the last layer, but it's not necessary for the analysis. Yeah. So basically, we have like a random task, a new downstream task. We see few samples from each one of the classes. We get some model based on these samples, and we measure its performance in expectation on new unseen samples from P, from the target task, the downstream task. Yeah, that's a good point. So let's think of learning, right? Like in standard machine learning, we have some training data, right? And we have test data. So in test data, you have like, let's say 1,000 samples, and you average across them, right? This is like the test. When you take expectation, it's like computing the test. You don't just test on one sample, right? So you don't test on one task the same way. And for simplicity, we will use the following like classification rule. So this is like the nearest class center classifier that I actually proposed. We will use that classification rule on top of F with the centers given by the few samples. So we have few samples for each one of the classes, look at their centers in F space, and we compare a new sample to each one of the classes, and we take the minimal distance. So the idea for how to analyze this, this problem, how to prove that, that like transfer learning works in this setting is to argue the following. So we want to bound or to minimize the FewShot error on new tasks, right? And we try to approximate it with the averaged FewShot error between source tasks, source classes. Okay, so we have the FewShot error between new unseen classes, and we have the averaged FewShot error between classes that we trained on. Okay, then we say, well, we don't have full access to the source classes. We just have data. So we need to bound this thing with the empirical version of it. Okay? So we look at the FewShot error between pairs of source classes, and we'll try to bound it with the FewShot error on the source data. And finally, we will try to connect it to neural collapse. That's the last step. So we'll say this quantity, the FewShot error, is bounded by the degree of neural collapse on the source data. Okay? And if we had neural collapse on the source data, which is the data that we trained with, then this quantity is supposed to be small. Okay? So this is small, then this is small, then that is small, then that is small. So the selection of S of Si and Sj tilde are like MIID samples from each one of the classes. Yeah. And that is measured like you select subsets of these big sets and you measure the same quantity. It doesn't make a lot of sense as a quantity, but it's useful for the derivation. So that is kind of like the idea. And this is kind of like the first step. Okay, so we have the expected FewShot error. We can bound it as follows. So what do we have? So we have the averaged FewShot error between the source classes, okay, plus some quantity that depends on the complexity of F and square root of the number of source classes. Okay, so the more source classes we have, this quantity decays, right? And then if this is small, then we expect that to be small as well. Okay, so we can bound the expected FewShot error in terms of the average FewShot error with some gap that depends on the number of source classes that we encountered. CF is like the norm of F, so like the product of the Frobenius norms. Yeah, I didn't want to get too much involved, but yeah, so this is kind of like a measure of complexity of F. And the second step would be to bound each one of these terms that we averaged. So it's very similar. So we have something that depends on like the empirical version of it. Okay, so this is like an empirical approximation to that. And we have, again, some measure of complexity of F relative to the number of, the square root of the number of source samples per class. Okay, so if we see many training samples from each one of the classes, then this quantity is supposed to be small, and this is a good approximation of that quantity. Okay, and M is the number of source samples per class, and N is the number of target samples per class. Okay, so N is much smaller than M, so this is approximately 1, and this is a constant here, this is much larger, so it's all good. And the last step is to bound the FewShot error in terms of the normalized variance. So this is kind of like applying Chebyshev inequality many times, but eventually we can show that the normalized, the FewShot error is upper bounded by something that is proportional to degree of collapse, the the clustering, the degree of clustering between the two classes. Right, this is, it's a great question. So basically, neural collapse is like a property of optimization, right? Like if I train a model on some predefined data set with labels, and the model is complex enough, it's going to collapse, right? So what you're saying is, well, if I train on a data that doesn't make any sense, like the labels are like they're nothing, they're just randomly selected, then how would that be useful for transfer learning? And I think that is hidden here. So with random labels, in order to fit the labels, the complexity is just going to be too large, and the bound will not make sense. That's what I think would happen. Yeah. Intuitively here, so basically we have like the how much can I distinguish between two classes that are relatively clustered. So if we have two classes, Qi and Qj, that are clustered in space, then I don't need to see many samples in order to distinguish between the two classes. This error Qij measures how good would the classifier that only sees few samples from each class is going to be on average. And that is kind of like intuitive, that would be small if the two classes are clustered in space. And putting everything all together, we get the following bound. So we have the FewShot error, the expected FewShot error. It is bounded by the degree of collapse, something that is proportional to the degree of collapse, plus two terms that depend on the complexity of the model, the number of source classes, the number of source samples per class, and also like the distance between the classmates. Okay? So essentially, if the model's complexity is not too bad, and I see many source classes and many training samples per class, then if I have neural collapse, I generalize to new tasks with few samples, okay? With a constant number of samples. Okay, any questions? Yeah. It's so the derivation of these bounds is based on Rademacher complexities, and just to get an end-to-end bound, we investigated what happens with like neural networks, but it could work for any other model, assuming that the neural collapse is a sensible assumption in that case, but it doesn't always happen, right? Yeah, you need like this. You don't need the perfect equiangular, but you need these distances not to be very small. So the fact that we have NC2, like this property of these distances maximized, is actually in favor of in this bound. Yeah. So yeah, it could hold for a broad set of models. Yeah. So yeah. So in terms of experiments, we wanted to validate that like this approach is useful for FewShot learning, which is in itself non-trivial, but also wanted to kind of like see how it behaves and everything. So we have two phases. In the first phase, we pre-train a model using cross-entropy loss minimization on a set of source classes. And in the second phase, we take the pre-trained model and we train classifiers on top of it with 5 classes and 5 samples per class, let's say. And then we evaluated these models on new test samples, and we averaged. So we can kind of like evaluate on many tasks. Okay, so basically, everything in red is different variations of this very naive approach. Anything in blue is like methods prior to us that do something very similar to transfer learning, but typically with like additional losses or constraints. So they're a little bit more involved. And anything above that is a FewShot learning, a classic FewShot learning method. So the other approach that I described at the beginning. And we can see that on a variety of data sets, this very simple idea is able to be either competitive or even better than FewShot learning methods, and also kind of competitive with the more complicated versions of transfer learning. This is kind of surprising to me because the model was not predefined, was not designed to solve FewShot learning problems. And it is able to compete against models that were trained to do so. And then we looked at to what extent this normalized variance generalizes. So basically we plot the normalized variance on the source data with varying number of source classes. Then we see how it generalizes to new test samples, how it behaves on the test data, how it behaves on new unseen classes on average, and also the 5-shot performance on new target tasks. Okay, so if we train with more source classes, then the degree of neural collapse on the source data is going to be worse, which makes sense because we added more classes, the task became more complicated. There are more classes, the task is more complex. The degree of generalization to new unseen samples is quite good. Like they are very similar. And we see that with more source classes, when training with 60 instead of 10 source classes, we see that the normalized variance improves. So if we trained with more and more source classes, then the normalized variance also generalizes to new classes well. And that is in correlation with what happens with the performance itself. So if we look at the performance, it improves when we trained with more and more source classes. And for completeness, we also looked at the minimal distance between the class means, which was in the denominator of the bound. We see that we plot this value for different learning rates, and we see that in all of these cases, the distance grows, and it's not close to 0 or anything like that during training. And it also improves with like the learn as we take the learning rate to be lower, which makes sense a little bit because it's kind of like overfitting to the degree of to the collapse of the specific source task. It's not necessarily a good thing, but it happens. Yeah. So now the question is like, is collapses even necessary? Do you have any ideas? Okay, so I'll try to say what I think, and hopefully we can have a discussion about it. So this is kind of like a plot we already saw, right? Like we have two classes, and if we pick one sample per class, then they kind of represent the data well, right? Like if I learn a linear classifier between the two samples, then this classifier is also going to be good for the other samples. What happens if the data is linearly separable, but not clustered. So, but the neural collapse is not so good. So basically the variance is not low. So in that case, I could pick any random sample from each one of these classes, right? Like I could potentially take this one and that one, and then I can take the max margin linear classifier. That is maybe the best shot I have. So I take this green linear classifier, and then there are potentially many samples that I miss here. Okay, so just picking one sample from each one of these classes is not going to be enough. But if the variance is like, let's say 0, then one sample is enough, right? So that gives you a constant number of training samples that you need to see. And here, it requires more than just one sample or a constant number of samples. But that's a very different setting. Yeah, I think in terms of like robustness, right? There is an advantage here that is not being expressed in the theory that I demonstrated now. But yeah, I think so. Yeah, it's definitely an interesting thing to explore. So I think there are cases in which it's detrimental. But before that, about the zebra, let's say instead of animals, you have like a sequence of breeds of dogs. Okay, so you see one type of dog, then another one, and so on. And now you see a new one. Then if I know that the variance is low for each one of them, then I also expect the variance to be low for a new type of dog, right? That's the idea. And that idea also applies for like animals or like objects and things like that, given that you see a sufficient amount of classes during training. And you assume that the classes are independently and identically distributed. A new class. So the idea is like this. So in standard machine learning, you have like a training data set, right? We assume that they are just random samples, and the test samples are new, fresh samples, but they come from the same distribution. And the reason why we are able to predict the label of a new sample is because we know that, like, on average, the performance is good, right? Like the average is a good approximation. The average on the training data is a good approximation to the expected value of the error on nuance in samples. It's kind of like a very similar idea. Yeah. So basically, the task similarity is encapsulated in assuming that the classes come from the same distribution, which is like a very, like, it's an abstract idea in a sense. Like we don't always know how to measure if, let's say, two sets of samples come from the same distribution. Yeah, it's a full like theory in its own, like how to correctly do that. And about like the detrimental case, if let's say I have a model that was trained on 3 classes, super classes, and now I have like a fine-grained classification problem, that's the new task, and let's say we have 3 classes that lie within the same class. If the superclass collapsed, then I'm doomed. Like the pre-trained model is not going to be able to distinguish between these 3 classes. So I really need this assumption of IID-ness to get the guarantees that I showed. Like transferring from superclass to fine-grained will not work in this setting. So you mean like how new classes, what is the structure of the, what is the geometric structure of new classes compared to like the source classes? Yeah, I actually don't know. It's a very good question to think about, kind of like if there is some spanning or like geometric structure that is inherited and you could connect it to, or it's like this image of just like clusters in space. Yeah, it's difficult to visualize because it's like high dimensional spaces. Yeah, so instead of investigating the expected few-shot error, what is like the variance of the performance across different tasks? We looked at the variance only just to plot kind of like, error bars and things like that. But, like a deeper investigation and a mathematical analysis of the variance, I think, is a bit disjoint than what we did in practice, but I think it's an interesting question, especially when it comes to kind of like, you want to pre-train a model, you want it to be reliable, right? You want to know that if I see a new task, it's not just like on average, it's going to be good. If I need it, if I need to be confident that it's going to succeed, then yeah, I think so two things that could control here is the number of training samples that you have for the target. That definitely is going to change variance, right? Like if I see more and more target samples per class, then like the variance is going to decay there. That's one thing. Obviously, like if you see more tasks, then the averaging is more faithful. But yeah, I don't know for sure like what are the exact dynamics there, but it's interesting. All right, so to summarize, maybe it's an exaggeration, but I think it's the first proof for like transfer learning between two tasks. So we have like the source and we have the target, and we describe like a framework here, and we derive these bounds that are showing that we can learn new tasks with a constant number of samples, whereas previous results basically study a setting where we have many IID tasks and not classes. I think it can also have some implications to explainability. So basically, it gives us some notion of what kind of geometric structures and what kind of representations we want to have when it comes to transfer learning. And it gives some guidelines for transfer learning in terms of neural collapse, right? If we believe that neural collapse is a favorable property when it comes to transfer learning, then we can think of transfer learning in this specific setting in the lens of neural collapse. How can I improve collapse? How can I make the collapse not collapse too much, aka overfit the source data, and so on. Which layers should I consider? How deep the network should be? What kind of normalizations do I want to incorporate? And there are many different open questions that come out of it, like what kind of geometric structures do we care about when it comes to transfer learning? Can it be extended? Are there other structures that we could care about when it comes to like other notions of adaptivity? And I think maybe a very interesting question is how to extend it to like more contemporary settings, like self-supervised learning, where we don't just like train on a classification problem, but we have unlabeled data and we use that to pre-train a model. And that's it.